Well, thanks, Birgit, for the introduction. It's great to be here today at ICRA. My first conference as a graduate student, I presented a paper at ICRA. I won't say how long ago, but it was a very long time. It was about robotics. So now I'm here to talk about automation, and I think it's great because robotics and automation go well together, like peanut butter and jelly, maybe. Anyways, so this is a picture of our robotics building, and if you want to hear more about the robotics department at the University of Michigan, we're almost coming up on our 2-year anniversary, so happy to talk about that later. But today, I'm going to talk about digital twins. And digital twins are a hot topic. Everyone's talking about it, and I've seen lots of different definitions. So I'm going to start by telling you what we think is a digital twin. A recent publication counted more than 200 different flavors of digital twins. People are using them to talk about simulations, to talk about high-performance simulation models, to talk about data, machine learning, everything, digital twins. Very hot topic. But for us, well, first I'll say the history of digital twins. I think the term was first used in the early 2000s by a professor at the University of Michigan, actually, who was working about product lifecycle management. And he envisioned having a digital copy of the product that would follow it through the manufacturing pipeline and into its lifecycle, mapping the real space and the virtual space with data and information flow between the two. So I think of a digital twin, and we define a digital twin as a replica of a real physical thing. If it's just a simulation and it doesn't have a physical counterpart, it's a great simulation model, but it's not a digital twin in our definition. It also has to have a specific purpose of impacting its environment in its real way. You could think about it's an observer that's estimating the state of a system that a controller could use and have an impact on its environment. It does have a model. The model in a digital twin could be a very high-performance simulation model, or it could be a simple threshold that you can use to try to predict when the physical system is going to go outside of some sort of limit. So it does need to have a model that it uses to make predictions. Typically, the digital twin has some sort of subject matter expertise embedded within it that it is used to create that model and used to understand what the digital twin can do and how that output of the digital twin can be used to make decisions. And finally, I think if it's going to be a digital twin, it needs to be collecting data from its physical counterpart in real time. Now, what is real time? Again, it's going to depend on the subject matter expert. It could be every millisecond. It could be once a minute or once an hour. If you're thinking about predicting whether the temperature of an oven is going to go out of spec, you may not need to take that every millisecond. Once a minute may be plenty real time enough for the purpose. So really, it has this, you can see on this slide, it's got a virtual copy of a replica of a physical world that is synchronized with its real counterpart and uses data to make predictions that are useful. So just a few examples of the kinds of things that people have done with digital twins in manufacturing. And I'll talk about 2 of these examples in this talk. Unfortunately, with a half-an-hour time slot, there's not enough time to go through the whole gamut of things you could do with digital twins. But in a manufacturing environment, you see on the right-hand side there, everybody wants to increase the quality, the throughput, the revenue, and of course the profit, the bottom line for the company. And in order to do that, you need to decrease the cost, decrease the time, decrease the scrap, things that you make that don't satisfy the quality, as well as variability. So people have been using digital twins for a long time. They just have only recently maybe started calling them digital twins. And people have been looking at predictive maintenance for a long time. They've been looking at reconfiguration, virtual metrology, as well as supply chain optimization. So these are all things that have been being done for a long time in the manufacturing industry to achieve the goals on the right-hand side. But what we think is an opportunity for research, and I'll come back to this a little at the end, is can we build a framework that can put all these things together in a similar method to make it easier to deploy these types of solutions in manufacturing environments, maintain the solutions, and really have a bigger bang for the buck. So I'm going to dive in, and like I said, I'll give you two very quick examples of research projects that we've done over the last couple of years in partnership with different industries on how we could use digital twins for predictive health maintenance and reconfigurability. And then I'll wrap up with some future directions. So predictive health maintenance, you might imagine, is a big, important problem in industry because downtime is expensive. And most maintenance strategies in manufacturing are based on time. We do this once a week, we do this once a month, we change this part every year, et cetera. And so in order to minimize the cost of this unplanned downtime when things break, you over-maintain the system. So you fix things more often than you maybe need to. You might, when you drive your car, you're supposed to get your oil changed every so many thousand miles, probably more than it really needs, but you don't want to have it go too long and then it would break down. However, because you do this type of over-maintenance, because the cost of things breaking is very large. In the auto industry, for example, downtime is typically tens of thousands of dollars per minute. So you don't want to get into that time when it's going to take you a few hours to fix something and you can just see the money flying out the window. So you want to have a preventative strategy that can minimize the over-maintenance, but also minimize the breakage. And that's where the predictive maintenance comes in. And so there's a lot of opportunity you can see in predictive strategies, but why don't people do it more often? Well, the answer is it's hard to predict things, especially when there's a lot of uncertainty in the system. There is a lot of data available that you could say, well, let's use machine learning and put a machine learning model on it. However, because these systems fail so infrequently, almost all of the data is when the system is healthy. So you don't have a lot of those failure examples to train your machine learning model. So what can we do with mostly data that's good? So I'm going to talk specifically more about rotating equipment here because these types of pumps and motors are very common in many manufacturing industries. And some of these industries, like oil refineries and chemical plants, are running continuously, 24 hours a day, 7 days a week, every day out of the year. So they're designed to operate without interruption. There's no, planned downtime like in an automotive plant where every night they have an opportunity to do some maintenance. So they do often fail. So this is I'll say maybe not unique, but unusual in a manufacturing where you do have failure data, because it doesn't cost that much more to take the system down for an unplanned downtime than a planned downtime. The system doesn't usually break in a catastrophic fashion. If it did, that would be a different answer. So I'm going to talk, again, with what we think of as a digital twin. We want to have the data that's coming from the real-time process that goes into this digital twin of the process. And you can see there's no picture of a pump and there's no angle of rotation. But we're going to take some data out of the pump, and typically we're going to use a vibration measurement. And what we'd like to be able to predict about that is the state of health. So is it going to, is the motor healthy, or is it starting to degrade, or is it likely to fail? And how much time do we expect before it's going to fail? Because if we have that information, we can think about, well, would it make sense to take that down tonight or next weekend, or we're going to run it to failure? And that information can be useful for the operator. So based on this runtime data, we'd like to be able to identify the state of health of the system and the trajectory of that state of health. So here's a little data from a real-world example of a bearing degradation and failure. There's no scale on the vertical line. These are just intended, I mean, this is real data, but I'm not going to go into the details about the actual magnitude of the failure. But you can see I'm just taking the last 100 time steps. I think this is about 100 minutes, so this is not, millisecond data. And we've looked at the literature. You can see some of the references there, that there's some different typical types of degradation patterns. Does the vibration go up in a linear fashion? Is there an exponential trend? Are there some steps that it accomplishes? And each of these is a separate model. Now, when you start out, you don't necessarily know which one it is. And so we're going to use this idea that we have a model in our digital twin, but we're going to have multiple models. We're not sure which one of these is going to happen, but we're going to use the data to try to identify which model is a best representation of the system. So here's an example of a specific test. And this is what we have is this multi-stage health model. So we assume that the system starts out healthy, and then it can go into a shallow linear trend, a steep linear trend, or an exponential trend. But you see all the arrows out of healthy are only one way. If the system starts to degrade, it only continues to degrade. Now, depending on which trend it takes, it could switch between these different trends, and that's what those bidirectional errors are. And if it hits the fault limit or the out of spec, then it's done, it's broken, and we have to replace or repair it. So what we do is in the digital twin, we have all of these different types of models. And what I'm going to show you here is a video, or taken from the digital twin running in real time. And you'll see that as we're taking the data from the vibration, we have hundreds of different particles, it's a particle filter model, that are tracking which state of health we think it's in. And on the bottom, you can see our based on the number of particles, what's the fraction that are in the healthy stage, that are in the linear stage, or in the exponential stage. And based on those, we project forward. On the top, you can see when do we predict that the fault will occur. And you can see it's not perfectly accurate, because once it starts leveling off here, you see, oh, I don't predict a fault anymore. It may still be in the degrading phase, but it's going to take a while. And eventually you'll see that the prediction of the digital twin, eventually you can see that, oh, I'm predicting that it is going to fail after some amount of time, and my confidence in that is increasing. So you can see in the top plot, it shows the probability distribution of what the failure time will be, and at the end, it gets it, it's not too far off. So if you back up a little bit, if I can get my mouse over there, you can see that, it's not perfectly accurate, but once it sees that it's going to fail, you have a pretty good confidence that, okay, I have a little bit of notice that this is going to fail if I want to take some action. So in summary, we have this streaming real-time data coming into our digital twin that's populating these different particles that are tracking different probabilities of health state. So we estimate this health state with probabilities, and from that we can predict the potential fault time with some level of confidence, and that can be used to make some predictions that could be useful for a maintenance engineer. So one example of a digital twin taking real-time data and using it to make a prediction. So I'm going to talk very briefly about this idea of reconfigurability with an even simpler type of digital twin. So this came from some work we did with a company that's making a battery manufacturing line. So you can see what it looks like here. This is only showing the machines that are in there. But it is a mix of manual and automated operations. So if you take out that 51 different operations. They're split into 20 stations, and this is a little bit of a cartoon of what that looks like. And so what we worked with the company is this is on the bottom right, you see the mean operation time for each operation. So on station number 1 with this large robot, there's actually 3 different operations, and you can see that adds up to about 40 seconds. Station number 2 is a worker. There's a lot of little operations. The worker's putting all the different pieces together into a kit that then goes to scanned by the camera and the laser, and goes to the large robot that does some assembly. So you can see the humans do a lot of little things that take a little bit of time, and then there's some things that take much longer. So this is our model of the system that a person has put together, a subject matter expert. And then we can build a little simulation here. You could think of this as a model too, if I can find. And so you can see that the parts are going through and they're coming along the line. And if I could find my mouse, I could speed this up a little bit. And at the bottom right, you'll see how many parts you're making at the end there. So it's just a simulation. So you could think of this as a model. And so what we're going to do here now is, instead of building a digital twin of this whole plant, we're going to build a digital twin of every station. So we have 20-some different stations that are doing the 51 operations. And what we have is, based on the data that we've taken over this line, over however many weeks or months it's been operating, we have an expected time that each station takes. And you can plot that as a histogram. So this is our model. Very simple. It's just a statistical model. And so what we have is that we expect the amount of time that an operator takes at a station to be within this distribution. And if it's too long, then we might have some, so we're going to predict whether the timing that we observe at every operation, is it within this histogram or without? And if it's taking too long, there could be some problem with the person. Maybe they have an injury in their hand and it's just taking them longer to do it. And if they're just too fast, then they might be missing something. So that's also a problematic. So we want to make sure that they're operating within the expected time. And so what we can do is, if we do see some difference in one of these station operations, that the digital twin says, hey, I think this is 90% out of spec, then we can issue a trigger to a configuration planner that will reconfigure the whole line. And I'm not going to talk about how we do that, except that we have another method that comes up with different possible configurations, how we could change the line, and we use the actual data from the digital twins that we've built to build a new simulation to understand what the different possible outcomes of that new configuration would be. And then we present the performance of those different configurations to an operator, who then can choose, I'm going to reconfigure and assign task number 3 to worker 2, et cetera. And that goes into the factory floor, that reconfiguration, and then we continue updating based on digital twins. So this is a little bit of a contrived example that shows how that might work. So we have here worker number 2 shows up, and they're very tired. They got jet-lagged. They just flew back from Japan or whatever. And so they're working very slow today. And so they're taking 200% of their time on all of their operations. And what this means is then the cycle time is not being met. We're not making enough parts because we're waiting for worker 2. So we went through that reconfiguration process, and the decision was made to add on this robot to take over some of the work from worker 2 and put some of the tasks from operation 25, have worker 3 come over and help. So this is what that solution looks like. So worker 2 is this red line. You can see this is what their times used to be, and now they're much slower. And so the worker at the next station is taking on some of operation 25. You can see that split between 2, and the robot is taking on this purple. And so the digital twin is the one that allowed us to initiate that reconfiguration. And this is what the movie looks like if you move this along. And you can see, I need to get far enough. So you can see that some of the 25, operation number 25 is being done by this worker and others being done by the other worker. So they're swapping out who's doing what. It's taking extra time to go over and get that. But again, you can have this simulation built with the statistics of each operation to show that you're going to be able to make the right number of parts over each shift. So 2 very quick examples of how we can build digital twins. And the models I showed here were very simple, right? One was just a particle filter with regression, and the other was just a histogram or statistical distributions. But there's so much more we can do with digital twins. And so one of the things that we see as an opportunity is to put together the framework of digital twins. So we can have multiple digital twins of the same system. I showed you in the reconfiguration example, we're just looking at the time. You could have a different digital twin that looks at quality. And are you going to predict that the quality is going to be a good outcome for each worker, for each station, for each plant, et cetera? And so you think about hierarchies of digital twins that would inherit properties from one to the other and generalize. And then I showed a little bit in the reconfiguration how you would use these digital twins for predictions in what-if scenarios. I won't go through all of the illities, but these are good things that you'd like to have in a manufacturing system. So one thing that we're doing to address all those research initiatives is we're currently working to propose an NSF Industry University Cooperative Research Center with the University of Michigan and Arizona State University, and Wenlong Zhang is here from Arizona State. So he and I are working together to put this proposal together. And the idea is that we'll have industry participation and industry funding with NSF support to have pre-competitive research in these 3 thrust areas for digital twins. So you can think about building the frameworks and standards and coming up with different applications. And workforce development is a key feature of that. At the 2 universities, we have a few test beds that we use for these types of digital twins where we can run industry-relevant robots, machines, rotating equipment, putting them together so we can take our own data on our little factory floors as well as taking data from our industry partners. So if you want more information about our research center, I can point you to this website, or you can come talk to one of us afterwards. And anyone who's interested in digital twins, I'll recommend this report that came out from the National Academies last fall on foundational research gaps and future directions for digital twins. I talked a little bit here about manufacturing, but there's a vision that you could have a digital twin of the climate that you could use to make predictions about how the weather is going to change, digital twins in medicine, thinking about a digital twin of a cancer tumor and how different treatments might affect the growth. So lots of different interesting ideas for digital twins. So I want to just acknowledge the students and my collaborators that I worked with that did the work that I presented to you here. And with that, I'd like to thank you all for your attention and be happy to answer any questions.